So hello guys, welcome back. We are going to continue on our investigation into fluid mechanics. So in the last video we found that a very good guess for how K is related to how K is correlated to these geometry of the pipe. It can be summed up in a very simple relationship. K is proportional to L by D, and in fact that's how experiments have shown it to be, and they've shown it to be true. And it's kind of interesting, you see, like you can imagine the entire geometry of the all circular pipes can be condensed into just these two pieces of information, or this simple ratio called length by diameter. This is just a ratio. It's a ratio, and we know that it's dimensionless. Right? So instead of having circular pipes of various length and diameter, then you have to test for each one of their K. You can just have a simple correlation between K and L over D, and experiments have found it to sort of be linear, and that kind of helps you solve the having to perform a million kind of experiments for cylinders of all shapes and sizes. Now, what about this star shape? It's over here. What about this star shape? Well, we have seen that this 4 by D. Okay, let me go back to our content from the last video. Okay, we have seen that the area to volume ratio for a cylinder is 4 by D. Or in fact, since we have also found that the area to volume ratio is simply the perimeter, or we call it the wetted perimeter because the fluid is in contact with the entire perimeter. We call it the wetted perimeter. The wetted perimeter, the ratio of the wetted perimeter to the cross-sectional area. So I'm going to write PW over AXS equals to area over volume, and this area I'm just going to clarify. This area is the internal surface area. That means this dark colored line. Okay, right. This ratio is just described by such for a circle, and then we note that the diameter equals to 4 times AXS divided by the wetted perimeter, and we find that hey, for a circle, this ratio 4A over P will just give us the diameter. But let's say for other shapes, what does it give us? Well, we can use the same A over the cross-sectional area over the wetted perimeter formula to give us something called the an equivalent D value. Okay, it will give us an equivalent D value, and we'll call it the hydraulic mean diameter. So when you see fluid mechanics professor give you this kind of formula, you understand where it comes from, because we don't have pipes always in a circular shape, but we can give it an equivalent kind of a diameter called the hydraulic mean diameter to kind of give us an idea of what's important. Yeah. So it's kind of interesting, right? You have you have we have pipes of all shapes and sizes. It can be cube size, or a cylinder, or a star shape, or a square shape, cross section, and all of this geometry is well, at least from a fluid's perspective, distilled down to this ratio, the ratio of the length to the hydraulic diameter. Now, isn't that interesting? So for all geometry, all you need to know is this L by D ratio, and that will tell you a lot about how K will be affected. Now the question is it possible for us to do the same treatment with, let's say, a fluid? Well, the fluid will have lots of things that's going on. We will have, let's say, a viscosity, we will have density, we will have the fluid volumetric flow rate, mass flow rate, and then etc, etc, etc. And then you're wondering, hey, what are we supposed to do with all these information? Information. Okay, so let's break it down. Okay. Let's say m dot equals the mass flow rate equals the rho volume equals to rho, so it's equals to rho times the volumetric flow rate. So it will be the area of cross section and the mean velocity. And if you want volumetric flow rate, that will just be area times the mean velocity again. And then what else do you think it will affect? Maybe the thickness. This is the viscosity. Okay. What else? We have this. We have the cross-sectional area. We have mean velocity. We have all this. And then what else? Maybe this thing we found, hydraulic mean diameter. You probably guessed that, hey, this will affect the fluid flow as well. You never know. Okay, so yeah, these are some of the properties of a fluid. What else can we think? We have density, we have viscosity, we have temperature. But what ultimately does temperature affect? It will affect the density and viscosity. These are more directly related to the fluid. What else? See if you can think of any more. Okay. If not, we are going to put all these in. So in general, let's say we have a K, it will be some function of hydraulic mean diameter, mu, A, cross-section area, V min, and of course the length. And of course we have density as well. So that's like 6 factors already. Okay, we may or may not know what's more important, and we see that some of these actually repeat. We see volumetric flow rate appear here and here. So when we say mass flow rate, implicitly, like, the volumetric flow rate is already kind of included, so we don't want to do a repeat. So, and if we say mass flow rate, it kind of includes the density, the cross-sectional area, and the mean velocity as well. So if we say mass flow rate, we are implicitly saying all these are kind of affecting. So if we are listing down variables that affect it, we don't want to repeat them, because that will mean that we'll have more over here than more the K being a function of more of these things, and we don't know what's gonna happen. It's going to be very complicated for us to try and simplify things down. Now, of course, previously we have found that it's interesting that one of these so-called dimensionless groups, okay, this dimensionless ratio, the L by D, the hydraulic diameter ratio, the L by D ratio, okay, we found that it is very useful for helping us determine or describe all the geometric properties of the pipe, and it's very useful to help us correlate it to K. Okay, so since it can be correlated so well to K, are we able to find other of these, special ratios so that we can, generalize the results over, a lot of cases, and it prevents us from doing so many experiments? Well, there is a way, and that is what these videos are about. This is called dimensional analysis, and the method is called Buckingham Pi Theorem. Okay, it may seem very complicated, but let's break it down again. These pi groups, why he calls it pi groups, these are the dimensionless group or ratios that we are talking about earlier. Remember this L by D ratio? Yeah, this is one of the dimensionless ratio that's important for fluid mechanics. So what dimensionless groups can we find, and how are we going to determine, help us to churn out some of these dimensionless ratios? Well, let's see. Okay, so Buckingham's Pi Theorem, you can find it on Wikipedia. Okay, you can find it on Wikipedia. And this will be normally taught in fluid mechanics anyway, so alright. So what is it saying? More formally, the number of dimensionless terms that can be formed, P, is equal to the nullity of the dimensional matrix, blah 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 blah. Okay, don't worry about all these very scary sounding terms. So let's say we have K independent physical units. We are able to form a limited number of dimensionless group. What do I mean? Okay, so the formal statement is here. You can go and look it up on Wikipedia, but we want to put it in some layman's language. Well, let's say we are trying to find how many pi groups we can form. How many pi groups can we form? So Buckingham's Pi Theorem says, okay, let's say you have 6 variables here. So the number of pi groups, well, at most, we have 6 groups. But we need to subtract by a number. So what number are we trying to subtract it by? Well, the number that we try to subtract it by, it depends on the dimensions of these numbers. What am I talking about? Let's say dimensions of the hydraulic mean diameter. So what is this? It's a length, right? So the dimension in its most basic case is a length. What is viscosity? As we have found out earlier, mass, length to the inverse, time to the inverse. What is density? It is mass per volume. So volume is in a meter cube kind of thing. So it's length, mass per meter cube. What about velocity? And that is just length per unit time And what about, okay, we have this, we have viscosity, we need cross-sectional area. AXS equals to length squared, and the rho is at the back, and again you see length here again. Pipe length here is of course a length. Okay, so instead of saying L equals to L, I'm just gonna say pipe length. The units are in length terms. So what do we have here? We have mass, we have length, and then we have time. So we have mass, length, and time. Now if we had temperature, we would include it as well. Okay, but generally we'll assume constant temperature for simplicity. You can imagine if we're gonna keep adding lots of types of quantities in, we're gonna get more and more complicated situations. I see. And basically we have things in terms of mass, length, and time. Nothing else. These are what Wikipedia would say like the K independent physical units. What is K independent physical units? So now we have 3 independent physical units. One is mass, one is length, one is time. So we have 3 independent physical units. These are mass, length, and time. So K equals to 3 in this case. How many pi groups can we form? So the number of pi groups we can form, or the dimensionless ratio, that is equals to six minus 3 equals to 3. So we have 3 dimensionless groups that we can form. Now how are we going to find those dimensionless groups? Now we use something called, if you've heard of Rayleigh's method, we can use that. But I'm going to try something a little simple. And of course, yeah, we try and yeah, sounds noisy outside, but I hope you don't mind. Anyway, we will try to find these 3 dimensionless groups. 3 dimensionless groups. Okay, we'll find 3 dimensionless groups. How are we going to do it? Okay, so the general idea okay, so we have all of these here. Okay, all of these here, right? So we can find how these are grouped together. So let's write it like that. A. What's the next one? Mu. B. What's the next one? Cross-sectional area. A. XS. C. Next one. Mean velocity. So let's put V mean. V mean D. So, and then L to the power E, and rho to the power F. The point is not to solve for all of these, but you know, idea is that we want to find a way that we can make it such that the sum of all these A, B, C, D, E, F, or rather you want to make sure that at the end of the day, whatever groups that we put together, we want to make sure it's dimensionless. So let's say we have a length already. So okay, maybe this should be 1. It's not k. Yeah, so this is unitless. Alright, some unitless quantity will be equals to all of this multiplied together. That will help us find the dimensionless quantity. Alright, so let's put dh. Let's have dh in. So what's dh? Now you can have a equals to 1, 2, 3, 4, blah blah blah. But we'll have a simple one. Let's fix a equals to 1. So we have some unitless quantity equals to dh. That's just dh. And what can we put in to make this a unitless quantity? Well, the most straightforward idea is to get this L to be minus 1. So L minus 1. And that will just give us dh over L. Right? Because this is in length units, this is also in length units. You can see both of them divide each other out. So next one may not be so easy. We can just look at this. Let's get mu equals rather b equals to 1. Okay, so we'll have this. Okay, and what are the units of mu? Well, units of mu, it'll be useful to write everything up first before you start. Mass per length per time. Okay, so we want the unitless quantity to be some function of mu, which is in mass per length per time, and this will be to the power 1. Next thing we need to know is, okay, how are we going to get rid of these make it dimensionless? How can we combine all these variables to make a unitless quantity? Alright, probably see you in the next video because it's already very long. We'll continue our discussion in the following video. Thank you very much.